My name is Denis Boyda, and I'm working at data science team of Algorithmic Leadership Computer Facility. And today I will be speaking about profiling. So at our section, we have a few subsections. I will start with slides with some general information about profiling, some useful tips, and it will be followed up by two subsections with hands-on examples. In the first subsection, we will profile PyTorch scripts, and it will be some basic material just to introduce profilers, how we can use it, and some useful lessons. And after that, we will have some kind of real application. So we will train a GAN, generative adversarial network in Tensorflow, and we will try to profile and optimize it. So I will show you how much performance we may gain with the profiler.
There's a little pop-up box in the lower right-hand corner. Could you dismiss it?
I don't know how. Oops. I don't know how. Sorry.
It's covering up the lower right-hand corner of your slide.
Yeah, but not sure if I can cancel it. I don't know how to stop
It's not quite big enough for me to see. What is it from?
It's from PowerPoint.
Okay, it's gone now.
Yeah, but everything gone. Yeah, let me. What's going on? Slideshow. Okay.
Okay,
yeah.
we're good now.
Yeah, it should be working. Yeah, so let's start with the profiling. So profiling and optimization is connected. And when usually people think about profiling, they have in mind some optimization techniques and vice versa. But in reality, profiling is just a diagnostic tool. And it allows you to understand the performance issues, to measure some bottlenecks, some timing, memory cost, and it will not always lead to optimizations. Sometimes just needed to understand that everything is going right. Sometimes you can see that optimization is not worth your effort. So it's good to consider profiling as a cool diagnostic tool for doing it. There are a lot of different profilers which you may use and different views. So here, for example, I showed one is a text view, another one is graphic view. So you can use whatever you prefer. There is some motivation for profiling, and it's so basically the purpose and the aim which you have is always very important. So. And when you do profiling, you should also take into account for why are you doing it. And there are different reasons for that. You can either find some performance issues or do optimization tuning or even do some fine tuning. And depending on the goal, the time investment in this project may be very different. But profiling basically proposes a lot of different ways, and it may be very easy to do just first screening, and analyze your code maybe roughly with some uncertainties, but at least it will give you some overview of your code, and will show you if you have some performance issues, some severe performance issue, and or if everything is going on as you expected. Another objective, if you want to do optimizations, in this case, you want to modify your code, you want to profile different parts of your script, and you can also estimate some gains which you may obtain. Profile will give you amount of time spent in different functions. And if you know what this function is doing and how you want to optimize it, you can estimate how much improvement can be obtained if you optimize this function. You can also estimate how much time you can invest in optimizing this function and trade-off between time investment and gains which this optimization will give you. And finally, there is a fine tuning, and in this case, you may do really deep profiling. if you want. In deep learning, in profiling deep learning application, the way how you profile may also depend on your purpose, as it is training or evaluation. If you already know the model which you want just to run, for example, in your some scientific application, there is part which does some simulations, and this part may be approximated with some technique from machine learning. So if you know this model, if it is already trained, just take some part in simulation, you could want to optimize it with really high performance. And in this case, it may worth your effort. But another situation could happen if you're just in phase of exploration, you do not know your model, you do training, and in this case, your script may be modified pretty drastically. You can even use different data for this case. So it may be not worth to do some really deep optimization, but some useful trick which you'll consider today will be helpful as well. Yeah, it's also very important to have in mind how much effort you're going to spend on profiling and what gains will be. Some easy tips will be just increase the batch size. In this case, you will increase GPU utilizations, but unfortunately, sometimes it leads to lower quality model. So sometimes there is a trade-off between better quality model, better scientific goals, and just better utilizations, and you should have it in mind. You can estimate from profiling how much improvement you can obtain. Sometimes there is just one operation like data loading, and it takes around 90% of the time. And in this case, if you optimize this one operation, you will have huge improvements of your huge speed up. But in other cases, if you have some function which takes 15% of the time, and if you're going to spend months as optimizing it, it may not worth these efforts, since speed up will be not so drastic. Yes, there are some common problems and some common solutions to optimizations is good to have in mind. And the third thing is what you can see in profiling is large kernel utilization, which usually means good things that you do everything good. You load your GPU, you do not have some bandwidth problems with data or with a copy or communication between GPUs, but you should consider it carefully, and maybe it's reasonable to check in more details which functions spend some time in utilization, because it can happen, and it happened in my experience many times, that some function takes majority of compute, like convolutions, but they are highly optimized, and in reality, the time spent in convolution is really low. And some non-optimized function like matrix multiplication, if you do it with the wrong shapes, may result in a large spend in time, but in reality, just because it is not optimized operation, and you can improve it if you want. Another thing could be to consider some algorithmic improvements. Large kernel utilization may mean also that you do work which is usefulness. And in this case, it could be reasonable to think about algorithms. So for example, with sorting, with small data sets, you can use a trivial algorithm, which has better asymptotic, but works faster in low data sets. But for large data set, you could use a better algorithm. So it's something to have in mind. And you can do it only if you know what is going on in your code. Another common issue is the slow input-output operations. And it could happen if you previously had some data processing script, or you analyze data in Jupyter notebooks with NumPy or other packages. So you could grab this data analysis to your deep learning scripts. And in this case, IO operation could be not optimized because you do everything on CPU with NumPy functions. And it's good practice to use data loads, which are designed specially for preprocessing and data loading. There are such data loaders in PyTorch and Tensorflow. They allows you to do multi-threading, so they can simultaneously run several workers, which does loading and which do loading and preprocessing, and also copy data to GPU, such that when GPU needs for data, it will not wait for it, it just will do some computations. It could also happen that preprocessing takes some large time, and preprocessing often happens on CPU, at least for PyTorch. And in this case, you may have also bad performance because GPU are quite huge today. So one node has, in CPU GPU, one node has 8 GPUs and only 2 CPUs, I think. So it may be a problem. And in this case, you may use libraries which moves preprocessing directly to GPU. And NVIDIA Daily is one of such libraries. Another problem you may face is an extra copy CPU to GPU and vice versa. And it can always, it can, sometimes it can happen just because PyTorch and TensorFlow coverage is not so huge as NumPy. So sometimes it could be more useful to move data to CPU and just run some function on CPU because NumPy has it, but it may result in slow performance. So in this case, it's better to move all operations to device. Sometimes writing some primitive algorithms for your problem may be more efficient than using highly optimized CPU versions. Another possibility is to use number and CuPy. And if you cannot do it, it's also good to use to overlap computations and copy of a data such that you can do it asynchronously, and you use some multithreading for that. A low GPU utilization can be also a problem, and it's easily solvable by increasing batch size. And finally, using too high precision for your problem may also result in low performance. So we know that GPUs are designed towards there are Tensor core units, and GPUs are work in reduced GPU performance and reduced precision much higher. So it could be reasonable to reduce precision to float or maybe even to the half. There are special tuning techniques in PyTorch and TensorFlow. You can easily do it, such that with just reducing precision of your problem will increase performance maybe twice sometimes. Profilers, usually all profilers have some APIs which more or less similar, I would say. In the middle, we have just Python modules where you just run some profiler module as a Python module with your training script. It's quite easy to do it. It may be a good start for the beginning when you have some scripts, you don't know how they work, and you do not want to modify this code. So you may just run some Python modules with the script without any modifications, and it will give you some useful information. But you should have in mind that in this case, Profiler will also take into account some warming up and some initialization, so your result may be a little bit biased. But as far as your initialization time is quite small relatively to compute time, you will have good results. Another API is using context managers, where you define some profiler with some settings. You may configure profilers as far as you want, and you can do some model training inside. And finally, there is a decorator option. When you do some fine-tuning and some more detailed optimizations, you can profile some just particular functions, and you can create some labels in the code such that you could focus on some particular part of the code. But some of profilers, let's say majority of profilers, gives you two numbers, and usually there is timing called self time or self CPU or GPU time and total GPU and CPU time. There is distinction between that, such that CPU time is accounts only for operation executed directly in this function, while total without taking into account any subcalls. And total time takes into account everything that is going on in this function. So for example, some functions are just wrappers, and the wrappers just take some time, but basically there is nothing to do inside this function. The function just call another function, and in this case, total time will be huge, but self-time will be small. Opposite situation will be really some simulation function which does some simulation, does some operations, inversions, whatever it does, whatever it needs. And in this case, self CPU time will be large, but total time will be low. So there are general view, um, there are visual plugins for profilers. Now, fortunately, there is a plugin for PyTorch, and for Tensorflow it exists for a long time. And important message I would like to discuss here is that in execution side, total timing of your application have to be split into several sub operations like kernel execution, copy some data, sometime needed for runtime, etc. And if you run some application, like in this case, it starts at 1 second and finished at 7 seconds. So the total time is 6 seconds. But if you just sum all operations, you will have more than 6 seconds. So you should somehow take into account overlapping between different operations. And it is done using some priority mechanism, such that there is some priority, and we took into account the first operation, and after that we subtract this timing for all operations. For example, in this figure, the highest priority kernel has, so we take into account the time in kernel span. In this case, 7 minus 2, it's 5 seconds. And when we go to take into to measure timing for mem-CPI operation, which took 2 seconds, but we already took it into account because it's overlap with the kernel. So everything which overlap in the kernel has already been accounted, and everything overlap just will be 0. So mem-CPI in this figure will be 0. For when we go to CPU execution time, the part of it was overlapped with the kernel. So in the profiler, we will see only 1 second from this figure. So if you see some low mem-CPI time, doesn't mean that you do not spend time in mem-CPI, just means that you have a good overlapping in your application. Okay, that's it in the slides. Now we can go to hands-on examples. Let me open our slide and show you. Let me see if you can see it. No, you cannot. Yeah, I think you should see it now. Okay, so if you open our section, Profiling Frameworks, there are 2 subsections, as I said at the beginning, PyTorch Profiler and Tensorflow Profiler. So let's start with the PyTorch. So in this simple hands-on, we will have some simple demonstrations with really primitive scripts, and we'll try to profile these primitive scripts with different tools. Such tools include Torch Autograph Profiler, Torch Profiler, Torch Util Bottlenecks, and Python C Profiler. Torch Autograph Profiler is an old profiler used in PyTorch for a long time. And I think this will be deprecated in a future version. It's still working, but PyTorch documentation tells that it will be deprecated. And instead of it, we may use Torch Profiler. Torch Profiler was introduced recently in PyTorch 1.8, about 1 year ago, and it has visual plugin, which allows you to collect information to visualize it in a beautiful dashboard in Tensorflow. So everything is pre-installed already. So if you go to CETA GPU, get node, and load conda environment activated, you can run all the examples. I can also do it. Just maybe I can just copy. Yeah. While I'm requesting for the node, we can discuss first example. So in this example, it's really primitive. We just set default tensor type, default tensor precision, double precision. In this case, we use a ResNet model from Torch Vision, and we have some random input just for demonstration. In order to do profile, in this case, we use a Torch Autograph Profiler, so we input as a profiler, and we use it as a context manager. So in this case, everything which is beyond this context manager model input will be profiled, and results may be printed. It may be sorted by different things. So in this case, we sorted by CPU total time and limited to the 10 iterations. So it is the output. So be sure that you loaded correct on the environment. Yeah, it is a first example, version 0. So we go to PyTorch profiler, and there are different examples, and we run example 1, version 0. Usually first time it takes some time to load everything and to run. So while we're waiting, we can see just general view. There is self time, there is a total time. As I explained to you, total time just takes into account everything which is going inside this function. So in this case, A18 conf2d, it does no work. So self CPU time is 0. It does nothing, but it just calls another function. And it seems that second function it calls is 18 convolution, which also does nothing. So there is another call with the underlying convolution. After that, there is a call of convolution non-group, which sum of implementations of convolution. Finally, we see colon of torch, ch, and then conf2d, which some native algorithm for convolutions. And it calls CNN conf2d forward. So we see that this method, it takes total time is 80%, but 30 time is spent on in real computations of this method. And second part of this time, which is 49%, it seems it's spent in the add multiply function. So it's some native implementation of PyTorch for convolution. So no kernels were executed. And there is also a batch normalization function. So you can see it further. Yeah, we just executed it. Here's more or less same input. What we can also do, we can basically see the shapes. It may be useful if you profile in some models and you don't want to make labels. So one possibility of profiling different parts of a model will be making labels to different layers of a model. Another thing may be grouping by tensor shapes, because in the ResNet, different layers, different convolutions have different input shapes. So if we add here record shapes in the profiler and group it by shape, we may see this output. I can run it. Yeah, so in this case, there is a first conf2d layer. This layer takes about 30% of the time, and it has input following input shape. So that's batch size, that is channels and some width and height of the image subcalls. And finally, there is another layer of convolution which takes another input. So it's another module of a ResNet. Similar output in here in example. It may be reasonable to analyze memory allocations. Which part of a program allocates which memory. In this case, you need to set attribute profile with memory. This example number V2. Yeah, so the majority of memory was allocated in resize function. Some memory was allocated in empty function. There is something in max pooling, and you can see other things. So it may be reasonable if you face some memory limits in your program. So you may execute you may try to collaborate on it and improve performance. So now let's have a look at our example more deeply. So basically, our first profiler shows it's here. We use native implementation of PyTorch, which is CHNN const2D. But we know that PyTorch has different backends. So for NVIDIA GPUs, it is a CUDA backend, and a lot of libraries from CUDA. For NVIDIA, there is backend also for AMD GPUs, and for Intel, we know that in Intel CPUs, there is a backend MKLDNN, which is specially optimized for Intel CPUs. And we should see basically the colon of MKLDNN in the profiler, but we didn't. And if we go to documentation to MKLDNN library, we can, because it's possible that some of operation was not implemented, and we can have a look on documentation and see which operations have been implemented, such that this operation should be appeared in a profiler. So we will see that convolutions are implemented, but only for float precision. And in our script, in the very beginning, we set a precision to double precision. So it prevents PyTorch colon MKLDNN kernels. So if we change it, I think it should be 3. Yeah, if we change it, so if we just eliminate this line, by default, PyTorch use float precision, and run it, we will see the call of MKLDNN. And in this case, timing will be lower than before. Yeah, so again, convolution 2D, some wrappers for convolution, and we see call of MKLDNN, which does all the work. You can see there is nothing, there is no more call, so it's a kernel. And so before, PyTorch used CHNN, const and batch and add multiply for matrices. Here we use MKLDNN, and the timing is better for that. Now let's consider another example of profiling. In this example, we have some simple model. In this model, we have, so it's here, we have 2 layers, sizes. So we have actually size layers, linear layers with activation and sequential. So we sequentially apply linear layers, so it's fully connected layers. In a forward function, we sequentially apply it, we obtain output, and we just demonstrate a problem where we want to compute some threshold, which will be output. So we compute mean over all channels of our output, and we compute so we compute sum of over all channels of our output. We compute mean over batch size. It will be our threshold. And we have also some mask. So we want to compare a mask with a threshold and obtain indices where it satisfies or not. So we can train this model in order to increase or decrease threshold. It is our training. Basically, we set up precision to float in this case, and default device to CUDA. We initialize input, initialize model, initialize mask. We do some warming up, because during warming up, some convolutions algorithm may be chosen, and as well as some increase in frequencies, etc. So usually the first iteration of profiling is not really reasonable. And after that, we do our profiling. So if we have a look on the profiling, we see here 2 sections. So it's another cool feature of profiler, such that we can add this labeling. We can add this labeling to another parts of a code. So in this case, we try to measure which time is spent in linear operation, which is two fully connected layers, and which time is spent on this simple operation with the computation of threshold. So before profiling, our expectation would be that majority of time is spent here in linear operation, because it has much more compute than this operation. But in profiler, we see that masking basically takes majority of time, while linear path is really small. So something is going wrong. And if we have a look on other functions, we will see that memcpy operation has 16% here. It means that we do some copy between CPU and GPU, and this copy is going on here. When we compute threshold, we compute NumPy argware function. We do it because PyTorch doesn't have this function. So we move data to CPU and compute it. But it is basically the bottleneck of this application. We see that if we eliminate my copy, in this case, we will improve our performance by order of 16%. So in order to do it, we can basically change our algorithm. Instead of argware, we can compare a mask with a threshold and compute not zero function, which exists in PyTorch. If we do it, the first important observation which we see is that that now there is a different functions, of course. Linear path now takes 22%, and there is still some memcpy operations. But another important point, the total time in this case 2.6 seconds, milliseconds, while before we had 2.3 seconds. So we improved performance of our application by approximately 1,000 times. And from Profiler, it was not clear that it could happen, basically, because we tried to optimize on 16%. So it's an important lesson we should learn. And the reason for that is that PyTorch Profiler optimizes profiles only PyTorch operations. And in order to profile all operations, we need to use other profilers. One of these profilers is Python C profiler. Maybe I can show how to call it. It's pretty easy. You just need to call Python example 2v2. And in this case, you will see this trace. Example 2v2. Example 2v2. Yeah, it's all trace of all functions and subroutines. So we see that they have really high-level functional call implementation. There is after that we call forward method of our script at line 24, and after that there is argware function which takes 1.9 seconds. And the real problem in this was basically calling argware, not the copy data between CPU and GPU. And we only, by luck, just optimize it because we eliminated it as well. So another important observation could be if we go further, we will see that there is argware, numeric, and internal implementation of it is basically non-zero method of NumPy array. So basically our implementation was reasonable because NumPy also use it in this application. Torch util bottleneck is another nice feature. In this case, we do not modify our example. We just call torch bottleneck as a module. Just run it while I'm speaking because it takes some time. And torch util bottleneck runs different profilers. It runs C profiler, autograph profiler with the CPUs and GPUs metrics, so we can examine all your code from different perspectives. But important point that in this case, profile doesn't exclude warming up of models, and in this case, you may have some bias to initialization, so you should have it into account when you see the profiling results. Now I just would like to show you how PyTorch Profiler works, which has a visual plugin. In this case, it is also ResNet model, but there is different syntax on profiling. In this case, we need to set up activities, CPU and GPU is in this example. There is also a nice tool which called Tensorboard Trace Handler, which exports data in order to load them in Tensorboard. And there is a nice scheduler such that you do not need to call your model before profiler. You can just set up scheduler so that it will skip the first warm-up operation, in this case one operation, and it will profile only 3 operations. So it's another new feature. In order to run it in order to examine data in Tensorboard, you need to use special plugin, but I think it is installed in our environment. But if not, you can easily install it locally or copy it on the environment. Let me show how it works. It is example 3v0. 3v0. Yeah, so in order to run it, it will generate profile for me. And in order to visualize it, I need to run TensorBoard. So there are two ways of doing it. Either I can copy my data to my laptop and run TensorBoard locally, or I can run TensorBoard directly at the SITA GPU node or SITA login node and forward ports. So I prefer the second option. We call profiler. It generated two profiles, and now I can run TensorBoard. What correct on the environment. Okay, now I can run TensorBoard with the port I want. I need also this flag and specify logdir. While this is running, we need forward ports. We can do it with this operation. So on your local machine, we need change port to port where our TensorBoard instance is listening. Change user. And run it. It will request for our password. Okay, so channel was established. We can check TensorBoard if it's running or not. Let's check it. So on local machine, we need just to run localhost, the correct port. It's running, so everything is working. It's a PyTorch profiler plugin. There is some execution summary, as I explained, with these different operations like kernel. In this case, it takes majority of time, which is really cool. There is a time step breakdown. So we did profile every epoch. So there is 3 epochs here. Performance hits. In this case, there is nothing which PyTorch profiler recommends us to do. There are different views like operators. Here you can see device self-time, device total time. In this case, self-time span and convolution. CUDA DNN convolution. There is a host time. Basically, it is just wrappers for CUDA kernels. Some we can more detailed view on the CUDA kernels and a trace of execution. Let me turn it on for the beginning. So there are profile steps. Here you can zoom in, see what is going on. So this is just wrappers which call CUDA kernels. There is a SM efficiency, which is show you what GPU is doing. So it's working here and doesn't work here. You may see here, there is a particular CUDA kernels which we call, and you may turn on this option, which shows you basically which operation executed which kernel. So for example, here, there was a CUDA launch kernel, so just function which runs CUDA kernel, and there is a particular CUDA kernel which was executed under this launch. So it is how it's working right now. Now let's everything about PyTorch. Now let's move to Tensor, to profiling of TensorFlow operations. In this example, we will profile GAN network, so generated by the Tensor neural network, which will, at the end, will be trained to generate this kind of figures. So GAN consists of two networks, generator and discriminator, and we will try to profile it. In order to profile it, we need to run it, and in this example, we run it on the singularity container. In this case, it is a container name, so singularity exec means we execute this container. We bind some folders, and we run bash here. So if we copy it, just let me go to Tensor and run, and run Singularity. There is some warning because we can mount it on this read only. We're still in the same folder. So we need also export proxies in case if you run it for the first time, you will need to copy data and it will require access to the internet, and we can run the script train gun. While it's executing, there is already some output here. So we see that initial throughput was order of 200 images per second. So we will try to optimize it, and we will start with the line profiler. Line profiler, it's still executing. It's quite slow for the first time it tries to compile a model. So we see it's quite slow. Let's go to line profiler folder. If it is not installed, you can install it with a pip locally with the user. I already in a Singularity container, I do not need to execute another one. In order to generate profile stack, I need to run kern prof for my script, and it will do some operations for that. I need to wait, and it will generate some data. So when the output of profile was generated, I can see it using module line profiler for Python. So it's still going on. I can put Ctrl+C, and in this case, execution stopped, but profile will save all information it did, which is really cool. And I can examine it with a line profiler. So this output. So let's see the same output here. So we added some decorators to different parts of the script in order to profile them. So the first thing, the first function which we call train gun, it is pretty high level function. So sometime here large time is spent on some initialization, which is not important, and majority of time is spent on training loop. So we want to have a more closed look on train loop. So it is a profiling of train loop function. We see that a lot of time spent in forward pass and gradients computation, but majority in forward pass. So let's have a look on it. We already added all necessary decorators. So let's have a look on profiling of this function. In this function, we see that sometimes spent in real data. Let's have a look other, but okay, it seems that majority of time is spent here, and it is 2 orders of magnitude large amount of time spent here in this function. Let's have a look on this function. I can also open it in the terminal. This function. So we obtain some data set, and we do some random choice of indices and choose the indexes for the data. Let's have a look on again data set function. This is a function, and you may see the problem right here, such that we load data. So every iteration we load the data, and this is a problem with the script, which we should eliminate. So the good solution would be to move this function to some global scope, such that we have some data defined globally, and when we need this data, we just took the amount of data we use. So every train iteration, we will not load the data. In this case, we define the global data set, and in a fetch a real batch function, we just take the data we need. That's it basically. If you run this function, you fix. So before it was order of 200 images per second, and now if we eliminate it, we see that now it's 2000. So it's approximately 10 times improvement of this. After that, we can continue profiling. So we want to redo profiler in this case, and we also want, so the majority of time will be spent in forward pass function, And if you try to examine this function, we will see that time is spent and some initialization. And after that, there is a computation of discriminator loss, and must be somewhere. No. Yeah, some time is spent on discriminator or some time is spent on generator. So it's basically execution. When we have the calling, this calling, it means basically that the discriminator. So let me open source code. That is IFX. Oops, sorry. Yeah, so for example, class generator, after doing some initialization, when we call instance object, it basically calls this method call. And in this method, we have just sequence of some operations, batch norm, generator layer, which 2D convolution, some unpooling, etc. So it is sequential calling of some operations, and TensorFlow has ability to optimize it. So in computational graph, every time we call this this kind of function, the data is first of all, there is some time spent for execution. We already saw it. And second, the data is copied from global memory to some registers memory. Every thread does some work. It copies to global memory back. And after this, there is another operation. So PyTorch has TensorFlow has some optimizer, which basically may optimize this part of a computational graph and try to merge some operations together and also eliminate some time needed for execution of the kernels. So in order to see it, let's go to another folder, TensorFlow function. So basically, we can add just this decorator to the call functions. Let's see, the F function. Yeah, so we just added these two functions to two calls, and if you run it, we want to go function. We will see that instead of 2,000, we have now 71,000. So it's a huge improvement. It's because we eliminated this we eliminated this time needed for running kernels. Another part of this compiler is called XLA, Accelerated Linear Algebra. And it is another, so basically this part tries to merge different kernels together. And if we add it, so basically in order to activate it, we need just to add special environmental variable to TensorFlow. So if we do it, we will see huge improvements in the throughput in this case. Well, it's not so huge, but it's order of 10,000 images per second. So it's another cool improvement. I think it is everything we could do with the line profiler. So in order to go further, we can use TensorFlow Profiler. In order to run it in comparison to PyTorch, we need to, instead of using context managers, we need to use this methods like start and stop, which will start profiling for our operation and we'll stop it. So we need to go to the folder TensorFlow Profiler. And we can run it. Python train gun. Yeah. Yeah, it will start collecting some information. So visualization of this profiling can be also done in TensorFlow. yeah, so we need to do similar tricks. We need to run TensorBoard. In this case, we need to run it in compute node, and we need forward ports. Another option would be copy this data to locally. So this is what I prefer. So on my local machine, I do for port forwarding for my user. And I need to know to which host. So I already did profiling here. Profiler should be generated to logdir folder. So I exit from Singularity container. I put Ctrl D. I'm not in that folder. I go to folder Tensorflow Profiler, and I need to run TensorBoard. TensorBoard -- port. Bind all. Yeah. And simultaneously in different terminal, I run port forwarding. I need again to so you should be able to do it. And if you do it, you will see this output, and you can see all details as we saw before. So the final optimization, I don't have much time, so I just briefly mentioned that final optimization we may do is a reducing precision. And if we reduce precision, first of all, Tensor unit cores will be executed on GPU, which will result in high performance, but also we reduce the memory bandwidth. So if you run it, the final optimization will be order of, there is no here, but it will be much better. Yeah. So basically, unfortunately, I have to skip last section about reduced precision, but you will see a section on reduced precision, I think, in another with another person. So if you have any question, I'm happy to answer. It seems there is not so much time